We are going to optimize f of xy equals 3x plus y, subject to the constraint x squared plus y squared is equal to 10. Looking at the constraint, we know that g of xy is equal to x squared plus y squared. And based on our definitions of f and g, we know that del f is equal to 3, 1, and del g is equal to 2x, 2y. We set up our system of equations using the idea that del f is equal to lambda del g, and 3 then is equal to 2 lambda x, 1 is equal to 2 lambda y. Those are two equations, but we have three unknowns, and so our third equation is needed, and it comes from the constraint. And so equation 3 is x squared plus y squared is equal to 10. The techniques for solving for x and y vary per problem. It depends on what you're looking at, so I can't give you a step-by-step. Sometimes what works is solving for lambda and then equating the results together from the first two equations. What I'm going to do this time is take equation 1 and divide it by equation 2. And you may wonder, is that loud? Like, can you divide an equation by another equation? And the answer is yes. Provided the terms on both sides of the equation that you're dividing by, provided there's only one term on each side of the equation that you're dividing by. The result here is that we have 3 over 1 is equal to 2 lambda x over 2 lambda y. And so we see that the 2's and the lambdas divide out, and we end up with that x is equal to 3y. Substituting that value of x into the constraint equation will give us 9y squared plus y squared is equal to 10, from which we can conclude that y is equal to plus or minus 1. Y equals plus or minus 1 into equation number 3 allows us to solve for x, and we get that x is equal to plus or minus 3. At this point, we have to be a little bit careful about how we pair up our x and y values. From the equation x equals 3y, we can see that x and y have to have the same sign. Because of that, we care about f of 3, 1 and f of negative 3, negative 1, but we do not care about, for instance, f of negative 3, 1. Using our original function f, which is 3x plus y, we can see that f of 3, 1 is equal to 10, and f of negative 3, negative 1 is equal to negative 10. And we can answer the question by saying that the maximum value for f is 10, and the minimum value is negative 10. Because we can see using a graph what's going on here, I've done this using GeoGebra, and what we've got here is the cylinder, x squared plus y squared equals 10, and the plane, z equals 3x plus y. And then their curve of intersection, which I parameterized. And what we can see is that for the curve of intersection, the largest value is 10, the smallest value is negative 10. Next up, optimize f of xy equals x e to the y, subject to x squared plus y squared is equal to 2. What I would like for you to do is set up the system of equations that we get by setting del f equal to lambda times del g. Come back when you have the equations set up. Del f is e to the y times x e to the y. Del g is 2x, 2y. And so our first equation is e to the y is equal to 2 lambda x. The second equation is x e to the y equals 2 lambda y. And then we have a constraint equation, x squared plus y squared is equal to 2. I had you stop here because we need to do a little bit of analysis as far as what x and y can be. Because e to the y is equal to 2 lambda x, we can conclude that x can't be 0 because e to the y is positive. It'll never be 0. Looking at the second equation, x e to the y is equal to 2 lambda y, we consider what would happen if y was 0. If y, a factor on the right-hand side, is equal to 0, then that means that either x or e to the y is equal to 0. We know e to the y won't be 0, and so we can conclude that if y is equal to 0, then x is equal to 0. But we've already seen that x cannot be 0. Therefore, we conclude that y cannot be 0. Since we know that x and y can't be 0, we can divide equation 1 by equation 2. By doing so, we'll divide out the e to the y's, the 2's, and the lambdas, and end up with 1 over x is equal to x over y, which means that x squared is equal to y. Putting x squared equals y into equation 3 yields y plus y squared is equal to 2. And by setting it equal to 0 and factoring, we can find that y is equal to negative 2 or 1. At this point, a little bit of further analysis is required. Folks, we had already decided that x squared was equal to y, which means y is equal to the square of a number, which means that y cannot be negative 2. Since y is equal to 1 and y is equal to x squared, we have that x is equal to plus or minus 1. Going back to the original function that we are optimizing, f of xy equals x e to the y, we can see that f of 1, 1 is equal to e, and f of negative 1, 1 is equal to negative e. E will then be the maximum, and negative e will be the minimum. You know what, when I circled negative e as minimum, I lost my negative there a little bit. Sometimes that happens in tests that I see from students. So make sure that when you're writing something down, you don't actually accidentally obscure it when you're presenting it.